This is Saravji with a educational talk about feature selection and feature engineering. In this part, I'm going to be demonstrating the feature selection demo notebook that I created. I'm starting out with initializing, loading the packages and setting a few parameters for the environment. Then I'm creating a listing of all the machine learning algorithms that I'm going to be using for this demonstration. Next, I am creating a couple functions that I'm reusing throughout the notebook. Most notably, actually, the score MCC function, which is the implementation of a Matthews correlation coefficient scoring function to use for evaluating the performance of the machine learning algorithms. Next step is to load the dataset. Then again, this is the stack of algorithms that I'm going to be using. I'm reviewing and linking to the Matthews correlation coefficient on Wikipedia. For convenience, this is the mathematical formula that I'm using. And then for each experiment that I'm doing, I am capturing the output in this table format to always have the same formatting that we can easily compare the individual experiments. Next is a little bit of data preparation and dividing up the data set between the target and the features. This first experiment is a completely naive approach. I am taking the full data set with all the features like it is and use the default algorithms, meaning I am using the algorithms how they are in the package by default, all default settings, but the only notable exception is I'm setting the random seed to have some form of repeatability here and comparability with that between the individual experiments. So that is the only one that I am setting every time if the experiment is not about modifying the parameters of the algorithms. So untuned algorithms are as they come out of the box. So then I'm running this naive approach, and these are the results that I'm getting. The best result is about 0.51 MCC score. And as can be seen, some of the algorithms are just not working in this kind of approach out of the bag. To make this experiment completely comparable with everything, I am not going to be tuning those to have some performance here. Next, I am doing a brute force approach. I am using a variation and combination of parameters to tune the algorithms, but still use the complete data set as it is. So there is nothing done on the data set. There is no feature selection, feature engineering done, nothing. It is the data set as it is out of the box, and then going through several combinations between all the parameters that I set in this approach. And going through all this, the runtime on a dedicated server that I'm running for these kinds of experiments was a bit more than 4 days. Close to 99 hours is the runtime to iterate through all these combinations. In comparison, the runtime for actually spinning up all the algorithms and getting everything up and running on the first time to run the naive approach is about 45 seconds. So there's a huge time difference here. Looking at the results, we are pushing the MCC to about 0.72. So that is quite an improvement there, but it comes at a cost of a lot of time that we actually have to wait for the results of this experiment. Next experiment is using univariant feature selection to select the most relevant features one by one. One of the drawbacks of univariant feature selection is that you have to define how many features you actually want to use. In this case, I selected, well, let's go with 10% of the features, so it's a relatively small number compared to the features that we actually have, so I want to have the best 10% of the features, which is 50 features, and then again run the complete stack of algorithms with those 50 best features, but an untuned algorithm, so the algorithm as it comes out of the box. The runtime is conveniently short, less than 10 seconds, and the MCC is already pushed to 0.63. So with the full data set, with all the features, untuned algorithms, we got 0.51. And with the univariant feature selection, selecting the 10 best features, we are getting 0.63, also in a very reasonable time. Next experiment is going to use recursive feature elimination. So we are eliminating features until we have a good remaining set of features, and then we're going to be using this remaining set of features, stack of algorithms, untuned. The runtime is a bit longer, 15 seconds, 10-15 seconds, so still very reasonable. And our Matthews correlation coefficient comes out to be about 0.61. So about the same as with the univariant feature selection approach. Next experiment is using PCA to reduce the dimensionality of the data. Now, with PCA, a common misconception that I'm encountering quite often is that we are actually reducing the number of features. This is not true, because if you actually transform your data set, you're reducing the number of dimensions. You're not reducing the data, the actual data that is in there. Because of that, it's actually possible to reconstruct the original data set out of a PCA-treated data set. And this tells you right there that all the information, and with that all the features that are in the original data set, are still available in PCA. Nonetheless, it's a standard stable in the toolkit, so running the experiment, treating the data with PCA, using the stack of algorithms in an untuned fashion. Runtime again is around about 10 seconds, so conveniently short. And the MCC that we're getting is about 0.55. So it's very close to the complete feature set and the untuned algorithm, the naive approach that we originally took, and it's not this clear improvement as we had with the univariant or with the univariant or with the recursive feature elimination approach. Next experiment I did is using a random forest classifier to actually fit all the data against it, and then using the feature importances method that a random forest classifier offers to select which features or how many features are actually important. So to recap, the sum of feature importances over all features is always 100%. So the higher the number that you're actually getting in there, the more important a feature is. So taking all 500 features, fitting it with the random forest classifiers, asking for the feature importances, I'm getting this kind of histogram. So as we can see, there are very few features here at this long tail with a high number of feature importance, and then there is a huge amount with very low feature importance. So the vast quantity of features in this data set apparently are not important. So I'm taking a kind of informed guess of somewhere in the middle here as a cutoff, and I am going to be eliminating all the features that are below this feature importance, so that I'm only ending up with the features that are with the high importance. And then I'm going to be using this this data set with the reduced number of features, in this way reduced number of features, and run it against the stack of algorithms with the untuned algorithms. And in this way I am pushing the MCC to 0.60. The complete total runtime, there is a little bit of manual work in here, and the complete runtime is a few minutes. So the actual runtimes are shorter, but actually it is required to put all this in there and evaluate it. So it is a few minutes to actually get this done, and then this way we actually can push the MCC to 0.60. But overall the MCC, so with the runner-up and the third placed, we are actually getting more algorithms that are coming into a solid MCC score here. Last but not least, I'm looking at a heuristic. It's the Bruta method. It is taking a little bit recursive and interesting approach on how to evaluate the individual features, and it's going through some iterations here, and it comes up, let's scroll down here. So it comes up with 21 confirmed important features, one that is still tentative, and 478 features that this heuristic rejects. So using this and creating a data set with only those 21 or 22 features and running it against our untuned algorithms. Again, this runtime in here is, let's say, 2 minutes to actually go through all these iterations and run it there, and then run it against with the reduced feature set, run it against our untuned algorithms. The runtime is below 10 seconds. And in this way, we are actually pushing the MCC. It's 0.77 here, then there is a 0.71, 0.68, 0.64. So we are getting into an area where we have a nice solid result across the board with quite a number of algorithms. Here are the feature selection experiment results in an overview. As mentioned, we're using MCC as evaluation metric. The naive approach, using all data and default models, is a best MCC of about 0.51, and firing everything up, spinning everything up, takes about 45 seconds to get the first result. Our next experiment was the brute force approach. So we're using all the data and we are tuning the models with just iterating over different combinations of parameters and try to find a good model or a good tuning for the model. The runtime is about 99 hours, so over 4 days, and our MCC did go up to 0.72. Then we have tried out univariant feature selection. So we are doing a selective data that we're using, and we're using default models, non-tuned models, and our MCC goes up to 0.63 in something around 10 seconds. Next, we tried out recursive feature elimination. So we're reducing the data until we can't reduce it anymore without affecting the performance. And we're using default models for that. And MCC, we ended up at 0.61 and the runtime of about 15 seconds. Next experiment, we use dimensionality reduction. So we modified the data and we're using default models and ended up with an MCC of 0.55, and the runtime was also somewhere around 10 seconds or just shy of it. Selecting important features with using a random forest and a informed guesstimate, I would call it, to subselecting the data to the more important appearing features, and using default models without tuning, our MCC gets to 0.60, and the actual runtime for fitting the models is less than 10 seconds plus a few minutes to actually set up using the random forest and doing the evaluation. Then using feature selection with the Bruta method, with comparing a feature to its shadow feature and selecting if it's worth it or not, and using only the selection of data, so the sub-selected data, and also running default models with no tuning, our MCC goes to 0.77. And altogether, for the complete pipeline, the runtime is just shy of 2 minutes. And like already mentioned, if I'm talking about default models, there is no parameter changed for the models. They are not tuned at all. The only exception to this is that I'm setting a random state that I have reproducibility and actually can compare the individual experiments.